A very good afternoon to all the students. I am Dr. HimaBindhu from the Department of Mechanical Engineering, and I'll be dealing the robotics subject. My today's topic is Euler Lagrangian formulation. What do we mean by the Euler Lagrangian formulation? What is the purpose of using this formulation? What are the various types or various methods involved in this formulation? And how we derive the equation to find out the motion of the robot's manipulator? All that we'll discuss in today's session. Firstly, what do we mean by the Euler's Lagrangian formulation? This particular Lagrangian is used to determine the model, or it is used to control the dynamics of the robot system. Right? That is, the Euler's Lagrangian formulation was being extensively used in robotics to find out the model and to control the dynamics of the robot system. This particular Euler Lagrangian formulation have come into action. This generally is used to determine the elegant method for in order to find out the equation of motion for the robot manipulator and mobile robots, or even for mobile robots. That is, it is used to provide a systematic and elegant method for determining the equation of motion. That is, this particular Euler Lagrangian formulation is used to determine the equation of the motion for the manipulators of the robot, or even we can use for the mobile robots. So here, this particular Euler's Lagrangian formulation has different applications. It's been applied for robotics in various forms. That is, in 5 different forms. One is the system description, Lagrangian construction, right, or derivation of the Lagrangian equation, control and trajectory planning, and simulation and analysis. So, firstly, let us discuss about the system description. What happens in the system description when we are using the Lagrangian formulation? That is, generally this particular type of the system in the robot is determined as the first kind of uh, it is the first kind which is used to determine the kinetic and dynamic motion of the robot. That is, the system description is used to find out the kinematics and dynamics of the robot's manipulator. It generally involves the configuration variables, where it reflects the use of the joints or links or the position orientation of the robot. That is, this particular type of the system is used to determine the configuration of the robot's links, joints, position or orientation, as well as their end velocities. That is, any robot's manipulator or the end effector has some velocity. Based upon that velocity, it has its motion analysis being done. So all that is being reflected with the help of the system description. Moving on to the Lagrangian construction. Here, this particular Lagrangian construction is generally being determined as the difference between the kinetic energy and the potential energy. That is, the particular robot will be developed with some kinetic energy as well as with some amount of the potential energy. So, the difference between this particular kinetic energy and the potential energy will give us the Lagrangian equation. That is, the robot system is then developed where the Lagrangian is commonly defined as the kinetic energy minus the potential energy, as I've told you. Generally in robotics, we determine the kinetic energy as K, or we can term it as T. and the potential energy is being written as Pe, or we can term it as V, which represents the effect of the gravity of the external forces. Right. This particular kinetic energy and the kinetic energy generally involves the translation or rotation motion of the robot's manipulator. That is the translation or rotational moment of the robot. For example, here we have a robot, right? This is the base of the robot. The translation as well as the rotational movement of the robot will be determined by kinetic energy, whereas the gravity and the external forces at the end effector, right? The gravity and or external force at the end effector will be determined by the potential energy, So basically the Lagrangian construction will be determined by the difference between the kinetic energy and the potential energy, where we also can write it as L is equal to T minus V, that is kinetic energy minus potential energy, where kinetic energy generally involves the translation or rotation of the robot's component, whereas the potential energy generally represents the effect of gravity or any other external sources. Right. Next, moving on to the next step, that is equation. That is deriving the Euler's Lagrangian equation. How we derive this particular Euler's Lagrangian equation? These are the steps where the robot will be following in order to determine its motion. Right? In order to determine its kinetic or the potential motion involved to move the manipulator, or these are the basic steps being involved. So the third one is derivation of the Euler's Lagrangian equation. So what happens here? What is happening in this particular derivation? Right. So this is generally used in order to find out the equations, which is used to determine the principle of the least action. That is, the robot's action, whatever will be determined, will be solved by the Euler's Lagrangian equation. That is, this particular equation is used to determine the action of the robot, that in which involves this particular equation involves the functioning of the derivation of the action, which is in the integral in relation to the generalized coordinates. Right? It is used in the generalized coordinates. So the derived Euler-Lagrangian equation are the dynamic equation of motion for the robot system. Right? This particular equation is a dynamic equation of motion for the robot system. Right. So any particular robot which is having which is moving with some motion, and which is where we need to determine its position or orientation, and any equation which has been determined by its dynamic equation of motion will be solved by the Euler's Lagrangian equation. Next, coming on to the fourth point, that is control and trajectory planning. What do we mean by control and trajectory planning? That is, here the control of the robot's manipulator or the control of the robot's trajectory planning will be done in this particular determinant, where it will be operated by a algorithm, right? Where this will be operated, the control system or the trajectory planning will be done by developing an algorithm and inserting that into the robot. So generally the resulting equation of the motion can subsequently be employed for the control. That is, the resulting equation is used to determine the control and planning, where this will be done by the planning algorithm, that is with the help of the algorithm, which manages the robot motion and completes its task. That is, by inserting an algorithm to the robot will complete its motion and complete the task whatever is being given to it, where the trajectory planning algorithm develops the feasible trajectory. Right. Um, Moving on to the next one, simulation and analysis. What do we mean by simulation and analysis? Here, this is the final step Right? The simulation analysis is the final step of the in order to know the behavior of the robot. Right? In order to know the behavior of the robot, we use the simulation and analysis process. So the Euler's Lagrangian equation is will be utilized to simulate and analyze the behavior of the robot. Right? The Euler's Lagrangian equation will be utilized. It will be used to find out the robot's behavior, which will be done by simulation and analysis. And this particular simulation analysis will be is a numerically integration technique, such as the forward and inverse dynamics, right? Such as forward and inverse dynamic simulation. So, by using this particular simulation and analysis, the behavior and the performance of the robot motion will be determined. The behavior and the performance of the robot motion will be determined. So, overall, the Euler's Lagrangian formulation will offer a systematic and elegant framework for modeling and controlling the robot system. In order to do modeling or controlling of the robot system, we need to have a tool, and that particular tool is called as a Euler's Lagrangian formulation. As I've told you, Lagrangian will be determined by the difference between the kinetic energy and the potential energy. And this particular equation is used to find out the motion. Right? This particular equation is used to find out the motion of the robot's manipulator. That is d by dou t into dou L by dou Q minus dou L by dou Q is equal to torque, right? Is equal to torque. Where using this particular equation, we will be determining the motion of the robot. Now, if T is equal to 0, then it is being said that the energy conservation. So if T is equal to 0, it is energy conservation, right? If T is equal to 1, then we will be having some other equations. So generally, we derive the total kinetic energy. The general equation for total kinetic energy will be written as kinetic energy is equal to, we know the formula of kinetic energy, that is kinetic energy is equal to half mv square, right? We all know that kinetic energy is equal to half mv square. So using the Euler's Lagrangian equation, how we determine this particular kinetic energy for a robot? So kinetic energy is equal to half sum of mi into q ci t ci plus sigma I to I omega power t into I ci. Right. So this is how the kinetic energy equation will be written using the Euler's Lagrangian formulation. That is, kinetic energy is equal to half sum of the mass m v square. Right. So that particular velocity, we in terms of torque, we determine it as q c I into t v c I power 0 plus sum of I and angular velocity, using the angular velocity omega t I ci I into dep omega, right? So generally this half mv square is for a scalar form, right? For a scalar form, we consider the kinetic energy as half mv square, whereas when we come across the vector form, it is half vt mv. right? Whereas when we go across the angular velocity, when we come across the angular velocity, half I omega square is equal to is the scalar form in terms of angular velocity, whereas half omega power t I omega is for the vector form, right? So generally for the Euler's Lagrangian equation, the kinetic energy will be written as this particular term, right? Kinetic energy will be written as this particular term. Whereas considering the scalar form and the vector form for both kinetic energy and with respect to the angular velocity, we will be getting these particular equations. Now the absolute velocity. Now in order to find out the absolute velocity, OVCI is nothing but the absolute velocity. Here we have, right, VCI is nothing but, this particular term is nothing but the absolute velocity, whereas ICI omega I to I is nothing but the corresponding angular velocity, is nothing but the angular velocity, as I have told you. Omega is angular velocity. So ICI, this particular term ICI into omega frame I to I is nothing but the angular velocity. Whereas for the potential energy, we all know potential energy, we all know that potential energy is equal to mgh, right? The potential energy is equal to mgh. So based on the Lagrangian equation, the potential energy will be written as mi g or sum of mi e power t 0 to 0 to ci, right? So based on the Lagrangian equation, the potential energy will be written as potential energy, the general potential energy is mass into gravity, that is mgh, that is potential energy in terms of the Lagrangian equation formulation, mi into g for a frame 0, that is for frame 0, into power the t into p of ci of 0. So this is how we write down the generalized equation for the kinetic energy as well as for the potential energy for the Euler's equation. Now let us consider an example, right? Let us consider an example where we are having a robot's manipulator, right? Let us consider an example where we are taking a robot, right? Where this is moving with some angle theta 1. This is the origin O, 0 to 0. This is for point M1. This is for point M2. This is the angle theta 2, right? This is link 1, link 2. And at point M, we have joint x1, y1. And at point 2, we have joint x2, y2, right? So let us consider an example for how we calculate the kinetic energy and potential energy and total Lagrange equation. So we all know Lagrange is equal to kinetic energy minus potential energy. So how we determine this particular kinetic energy, and how we determine the potential energy, and finally how we find out the Lagrangian equation will be determined by this particular example. So we have taken a robot which is having a we are taking a two linked robot, that is 2 degree of freedom robot, which is having an origin at 0 0, which is rotating at an angle of theta, and the link 2 is rotating at an angle of theta 2 with the joints x1 y1 and with the joints x2 y2, right? So generally the inertia I21 is equal to 0 and I22 is equal to 0. That is the overall inertia will be equal to 0, right? So in this particular example, the I21, that is the inertia at point 21 and inertia at point 21 and at inertia at point 22 is 0. So the total inertia will be equal to 0. Whereas x1 is equal to L1 cos of theta 1, where we can write it as L1 C1 and y2 is equal to L1 sine theta 1, where we write is L1 S1, and x2 is equal to L1 cos of theta 1 plus L2 cos theta 1 plus theta 2, where we write it as L1 C1 plus L2 C12. L2 C12, whereas y2 we write it as L1 sine theta 1 plus L2 sine of theta 1 plus theta 2, where we write it as L1 S1 plus L2 S12. So when we are taking the origins x1 and y1 or x2 and y2, based upon this particular equation, that is when we consider x1, how is it rotating this particular equation? L1 cos theta 1, right? This is L1 cos theta 1, whereas y2 is L1 sine, it is rotating beyond, so L1 sine theta 1. And x2 here, it is the combination of link 1 and 2. So L1 cos theta 1 plus L2 cos theta 1 plus theta 2. That is rotation of the manipulator will be taking place with respect to the two angles. So L2 cos theta 1 plus theta 2. So that we determine as L1 C1 plus L2 C12. Whereas Y2 is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. That is L1 S1 plus L2 S2. Now, we need to determine the x1, y1, x2, y2. Of the in this particular term, we will be writing the equation. So, the kinetic energy is equal to half m1 x1 square plus m2 x2 square plus m2 y2 square plus m1 y1 square. So the kinetic energy generally it is half mv square. So with in terms of xy terms, we write it as half mv square, that is x1 square plus m2 x2 square plus m1 y1 square plus m2 y2 square. So these particular x1 y1 x2 y2, when we substitute in the kinetic energy, what will we get? Kinetic energy is equal to half m1 of x1 square plus y1 square plus half m2 of x2 square plus y2 square, right? So when we are substitute this x1 y1 x2 y2 in above equation. When we substitute all these values in the above equation, what will we get? Kinetic energy is equal to half m1 l1 square theta 1 square plus half m1 l1 square theta 1 square half m2 l2 square theta 1 square plus half m2 l2 square theta 2 square plus m2 l2 square theta 1 theta 2 plus m2 l1 l2 c2 theta 1 square plus m1 l1 l2 c2 theta 1 theta 2. So this is how we get the kinetic energy when we are substituting x1, y1, x2, y2 terms in the kinetic energy, that is half mv square. Now in the figure we can see and we need to find out the potential energy. Potential energy is mgh. So based on this, how we write the potential energy? Potential energy is equal to m1 g1 y1 plus m2 G2 Y2 or M1G, gravity will be only one. So M1G Y1 plus M2G Y2, that is G M1 L1 S1 plus G M2 L1 S1 plus G M2 L2 S1 2. So this is how we write the potential energy for this particular equation. Now what is Lagrangian equation? Kinetic energy minus the potential energy. So this is the potential energy, this is the kinetic energy, and so in order to get the Lagrangian equation, L is equal to kinetic energy minus the potential energy. So L will be equal to half m1 l1 square plus m2 l1 square plus m2 l2 square plus 2 m2 l1 l2 c2 into theta 1 square plus half of m2 l2 square theta 2 square plus m2 l2 square plus m2 L1 L2 C2 into theta 1 theta 2 into theta 1 theta 2, right, minus G into M1 L1 plus M2 L2 S1 minus G M2 L2 S1 2. So finally what we get, tau is equal to d by dt of dou L by dou theta 1 is minus dou L by dou theta 1. So this is the actual torque equation. So d by dt into dou L by dou theta 1 minus dou L by dou theta 1, dou theta I, that we need to differentiate. So this particular equation we need to differentiate, that is dou L by dou theta I is nothing but m1 l1 plus m2 l2 plus just theta 1, this whole plus theta 1, this whole is equal to dou L by dou theta I, right? So in the, these are the terms which have been involved in the Lagrangian equation, that is dou L by dou theta 1 is that, dou L by dou theta 1 will be other, and by dt will be different. So here this particular equation should be determined, the this particular this will be determined as the units Newton meter. So this will be determined in Newton meter. Now substituting all these values, we will be determining the Lagrange's equation, that is kinetic energy minus potential energy, where it will be differentiated as tau is equal to d by dt into dou L by dou theta I minus dou L by dou theta 1. So using this, we will be determining the Euler's Lagrangian equation, right? So we're using that, we will be determining the Euler's Lagrangian equation. Now this will be determined for T1 as well as for T2, right? We will be determining it for T1 as well as tau 2. Right, that is for link 1 and link 2. And this is how we determine the motion or the dynamic or the kinetic energy or the potential energy of any particular robot's manipulator, or it will be determined by the Euler's Lagrangian equation, right, where it will be determined by a differential method, that is d by dt of dou L by dou theta 1 minus dou L by dou theta 1, right? So in the next class, we will be discussing about the Newton-Euler's Lagrangian equation. Right? This is the Euler's Lagrangian equation which was been determined in this form, that is kinetic energy minus potential energy. In the next class, we will know how the Lagrangian equation for the Newton was been determined. That is Newton's Lagrangian equation we will be studying. Right? Is it clear? So this is all for today. Signing off for today, Dr. J. HimaBindhu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.